Okay, hello everyone. Good morning and good afternoon. Welcome to the ASE section on statistics learning and data science monthly webinar. My name is Boxian Wang. I'm from the University of Iowa, and I will be your moderator. Before we get started, let me briefly promote two upcoming events. The first one is the conference Stake, which will take shortly at Harvard. Stake is the first time our statistical community has a peer-reviewed conference, proceeding, and challenge. The second conference is our very own SLDS flagship session conference in November in New York City. We warmly welcome everyone to attend those meetings. Now it is my greatest pleasure to introduce today's speaker, Dr. Alex Luke. Alex Luke is professor of healthcare policy and affiliate in statistics at Harvard University. Previously, he held faculty appointments in statistics and biostatistics at the University of Washington and Fred Hutch. Alex received a PhD in biostatistics from UC Berkeley and a bachelor degree in applied math from Brown University. Alex works at the intersection of semi-parametric, causal inference, and machine learning. Much of his work leverages computational power, be it through automatic differentiation, deep learning, or game theory, to automate the construction of efficient statistical procedures. He applied these methods as part of the multidisciplinary teams to improve decision-making in mental health and infectious disease research. As a mentor, he has supervised the completed dissertations of 8 PhD students, several of whom now hold tenure-track positions in statistics and biostatistics. Selected honors include a COPS Emerging Leader Award, NIH Director New Innovator Award, AMS Machine Learning Research Award. His work has been supported by NIH, NSF, PCURI, WHO, Netflix, and Amazon. Today's talk is on DoubleGen, Debiased Generative modeling of counterfactuals. Dr. Luke, over to you.
All right. So thank you for the introduction, and thank you to you and all the other organizers for inviting me. So today I'm excited to get to talk about some recent work on generative modeling, sort of at the intersection of generative modeling and causal inference. And everything I talk about today is joint work with Kenji Fukumizu at the Institute of Statistical Mathematics in Tokyo. He was kind enough to host me on my sabbatical. So I'll start with just a bit of background on generative modeling. I think it's getting sort of more and more familiar to many of us statisticians. It sort of has many of its roots in statistics, as I'll mention as I go. So broadly speaking, what is generative modeling? It's a paradigm for generating synthetic data that looks like existing data drawn from some distribution. And this underlies many of the recent advances in AI. So when one trains a chatbot like ChatGPT or something, the first stage, the pre-training stage, is essentially training a chatbot to imitate a large corpus of text. So this will often be like a cleaned up version of the internet or books or whatever. Image models are similarly sort of at their first stage. They're trained to just imitate large collections of images and sort of generate images that looks like ones in their training set. So I have one main running example today. That one will be in images, and I'll show a text example a bit later. So for images, a sort of canonical generative modeling problem. We're not at the causal inference stage yet. This is just sort of a basic generative modeling problem. We're given a data set that consists of a bunch of faces. Up until I tell you otherwise, all the faces in my talk will be real faces. Eventually, I'll show synthetic ones, and I'll make a point of mentioning it when I do. So we have a data set where we consisting of a bunch of faces here. There are maybe 48 or something. So a row in my data set is just one of these images. It's the RGB values across a bunch of pixels. I sort of put them in this rectangular form just so they'd all fit on the screen. And given a large data set, say several 100,000 images, we then want to train a model to generate new faces that somehow look like the faces we've seen before, but they're novel. So they're drawn from the same distribution, but they're not just sort of direct carbon copies of images in our training set. So the goal today will be to present a general approach for doing generative modeling, but instead of generating data that looks like sort of real-world data, we want to generate data that looks like counterfactual data. So data that we would have seen if we had intervened on the world in some way. And so in our example, the main intervention I'll think about is to generate counterfactual smiling faces. So all of the sort of faces in our data set that weren't smiling, we want to intervene in such a way that they are smiling. And roughly, this is an oversimplification, but if we wanted to sort of have a fully defined intervention, it's almost as though right before we took the picture, we asked people to smile, or we somehow enforced that they would smile in the pictures. So as a primary example, we'll use a data set, the Celebe data set. This is a common machine learning benchmark data set. The data set consists of, I think, roughly 160,000 images. They're a little higher resolution here. When I actually did my training a little bit later, I sort of coarsened the images a bit. They're at sort of 64 by 64 resolution for my later training. But alongside these 160,000 images, we have roughly 38 features. One of these features, they're all binary. One of them is whether or not people were smiling. And then we have other features in the data set, like whether or not people were wearing lipstick, had makeup, were perceived as female, as labeled by a human annotator. All of these were labeled by human annotators. Have earrings, no beard, blonde, etc. And what you'll notice if we look among the population of images that are smiling versus the ones that aren't, I've picked out some features here that are sort of different between those who are smiling and aren't. So 56% of smiling faces had lipstick versus 38 of the not smiling, 47-30 makeup, 65-52 perceived as female, 26-12 earrings, etc. Okay, so we have sort of meaningful differences in the frequencies of these different features. I should say the way we did this, we had, again, about 38 features, 37 if you don't include smiling. We ended up removing about 6 of those features that could have plausibly been impacted by whether or not someone was smiling. This would include like if someone had like crinkled eyes or something, if you smile, maybe your eyes crinkle a bit. So we sort of tried to pick out features that could be reasonably considered baseline features. This is a toy example. We did the best we could with the sort of data set that we had. But I think we can probably determine whether or not someone has a beard, for example, sort of independently of whether they're smiling. So that's truly a baseline feature that would occur before you choose to smile. Okay, so anyway, so we have these features. They differ among smiling and not smiling people. If I wanted to train a model that generated smiling faces, probably the easiest way to do it would be to take my 160,000 images, throw away all my images that aren't smiling, and just save those that are. And in the data set, it's roughly 80,000 of the 160 were smiling. And I just train an image model using those smiling instances. If I were to do that, I would indeed train an image model that'll generate smiling faces. But what it's going to do is it's going to learn to generate faces that sort of reflect the baseline characteristics of those people who were actually smiling factually in our data set. So roughly, you would expect that of the generated images, about 56% would be wearing lipstick, 47% makeup, etc. And that fails to match the overall population, where we'd expect 47%, 38%, etc. And here I'm just looking marginally. I'm sort of looking at marginal frequencies of people wearing lipstick or makeup. The same could happen sort of if you look at the joint distribution across these characteristics. We expect the joint distribution will be different conditionally on smiling relative to the overall population. Okay, so there's real confounding here in this particular image setting. You can actually sort of just see the confounding. We can see that if you just look at the smiling faces, more of them are wearing lipstick. Okay, so one of the goals of this talk is going to be to come up with a model, a generative model that's able to sort of imitate the overall population characteristics. So I'm going to start with an easier problem than the one I'll tackle later. So here we're looking at the oracle problem where all the observations receive the intervention. So this is a case where sort of we get to see the counterfactuals for each person of whether or not they're smiling in our main example. So ideally, we'd intervene and we'd collect a data set of counterfactual images. So we have these images here. This is the same sort of toy data set that I showed you earlier. Some of them are smiling, some aren't. When I perform my intervention, say this top left image, suddenly he will be smiling because I get to see his counterfactual picture when he's smiling. Okay, so once I have this data set, I now sort of am in a standard generative modeling problem where I can take my generative model, be it a diffusion model or whatever else, and I can train it to generate smiling images. Okay, and when I do this, I will indeed have an image model that will only generate smiling faces. And because I have now a sample of counterfactual synthetic smiling faces or counterfactual smiling faces above, I'll actually be sampling from the desired distribution. Okay, this is where I'm cheating here. I cheated when I went from sort of the actual data set I had to getting to see everyone's counterfactuals. Well, we'll deal with that in the next part of this talk to figure out how we get around this cheating. Okay, so to put a little bit of notation on all of this, in our oracle problem where all of the counterfactuals are observed, I'm going to suppose that I have access to n IID draws from a distribution boldface P. The boldface here is telling me it's my counterfactual distribution. So these are counterfactual draws from my counterfactual distribution. Then in this oracle problem, I can just apply generative modeling directly on those counterfactual draws to learn some transport map. So all generative modeling really is a way of learning a transport map that's going to take as input noise. So I'm going to call that noise U. It's just drawn from some known distribution pi. So that known distribution might, for example, be a multivariate normal or a high dimensional, say uniform distribution. And we're going to output this phi p. So phi p is my learned transport map applied to U. And that will have distribution P. Okay, so this is just a transport map, and this is really just, I'm just desiring that the push forward, when I push pi forward through phi P, that I indeed have distribution P. This is very convenient in a generative modeling context because it's very easy to simulate noise if that noise is multivariate Gaussian or something. And then all I need to do is just pass it through this transport map. We'll get to some interesting examples of generative models in a second, but in one dimension, there's really nothing to it. It's like a stats 101 problem. So if my outcome happened to be one-dimensional, then I could just take pi to be a uniform 0-1 distribution. And then my transport map would just be an inverse CDF. Okay, so this is just sort of standard inverse transform sampling, and that'll indeed give me a transport map. Okay, the problem is as soon as you push past one dimension, that this doesn't become so simple. You can't just use this sort of inverse CDF sampling. And especially when you're dealing with a high dimensional outcome Y, that's say an image, so it's very structured, but it's also high dimensional. It's sort of not always obvious how one could come up with a transport map that will actually follow the desired distribution P. Fortunately, there's been a lot of work on this over the last 10 or 15 years, probably starting with the GAN paper in like 2015 or so. So I'll sort of go through some examples now. I'm going to start with text for examples of generative models, just because it's very simple and it's something I think we've been seeing sort of in the news and in popular media for the last 4 years now or so. So here we have our outcome Y is a sequence of tokens. So it's a D-length sequence of token. A token is similar to a word. So what I did is I took the title of this talk and I just passed it through OpenAI's tokenizer on their website. So double is a token, gen is a token, the colon is a token, space deb is a token, etc. So we have this sequence of tokens. I could think of this as just a sequence of categorical variables where the categorical variable takes many values. I don't remember exactly, but I think there are roughly 150,000, give or take, tokens in this OpenAI tokenizer. So we have this sort of many-valued, many-leveled categorical random variable, and then we have a sequence of these values. So it's a way of just taking text and sort of turning it into natural numbers, essentially. Okay, and if I wanted to train a language model, we can do this as follows. So we're just going to try to learn a value theta. I'll say a little bit more about theta in a second. And it's just a minimizer of some loss. And here we're going to use the sort of guess the next token sort of formulation of language models that's very popular. Formally, this would be known as an autoregressive language model. So here our loss function is just going to be a cross entropy loss, where we sort of first look at the marginal probability of the first token, and we try to predict that probability. So this piece of theta here is indexing that probability. Then we want to learn the conditional probability of the second token given the first. Then we want to learn the conditional of the third given second and first, etc. Okay, so it's this sort of very simple formulation. So all we're doing here essentially is multinomial logistic regression. There's really not much going on in terms of the cross entropy loss here. I'm going to sweep out the details under the rug because they don't really matter for this talk. But in practice, you might parameterize theta as a transformer model and pool across time points. But that really doesn't matter. All we need to have is some way of parameterizing this conditional probability p theta via this vector theta. But in practice, this theta might be sort of a high-dimensional vector consisting of neural network weights. Okay, so we're going to use statistical learning to estimate this theta. And then once we have that estimate, we just need some way of doing sampling. And for an autoregressive language model, it's very simple. We just sort of sample one token at a time, conditionally on the previous ones. So first we'll sample the first token, then the second given the first, etc. And you'll probably remember many years ago, you could sort of see this very, very clearly in real time, and you would sort of work with ChatGPT, and it would sort of slowly produce one token after the other, and you could sort of see it happen in real time. They're obviously a lot faster now. They have sort of faster, sort of clever ways of sampling. But broadly speaking, all these autoregressive language models do is they sort of sequentially sample tokens conditional on the previous ones that they've generated, where the probability distribution that they use is parameterized by those neural network weights that we learned in the first step. Okay. Okay, so that's sort of one generative model that we just went through. I'm going to just sort of rewrite what I just wrote down as a very simple algorithm. It's only a few lines long. And that's going to turn out to capture that autoregressive language model that I just talked about. It also captures models that you might use often for images. So it captures diffusion models and flow matching as well. Where here we have an algorithm that takes as input counterfactual data. And then we're going to require a few things. We're going to require a hypothesis. That's that theta that we learned on the last slide, like those neural network weights. And we're going to learn this via some risk minimization problem. So we have some loss function. Our risk is just the average loss. And then we're going to try to minimize that empirical risk. Maybe we do this via empirical risk minimization, or maybe we sort of do it approximately by something like stochastic gradient descent. And across sort of these different settings, on the last slide, we saw we can use the cross-entropy loss for a simple language model. For diffusion models, you're trying to learn a score function, and we use the denoising score matching loss, for example. And flow matching, you're trying to learn a vector field, and you use the velocity matching loss. And then at the end, once we learn this theta, we just need to have some way of sampling from it. So remember on the last slide, it was sample the first token, second given the first, etc. For a diffusion model, we might use a stochastic differential equation solver. And for flow matching, you can use an ordinary differential equation solver. So there's sort of these standard ways that sort of once you learn theta, again, in practice with high-dimensional structured data, theta is often just a collection of neural network weights. And then once you have that theta, we just need some way of sampling, and there's sort of standard ways of doing this across different popular paradigms. Okay, so we have this sort of very high-level way. It almost looks superficial to write the algorithm in this very simple way. But what we're going to do in the next part of this talk is sort of figure out how we can modify this Oracle algorithm so that we can actually generate counterfactual data, or generate synthetic counterfactual data, even though we don't have an IID sample of it. Okay, so here we'll turn to what we're calling our factual problem, which just means that essentially some observations don't receive the intervention. We have observational data. The intervention wasn't randomized, and some of the observations didn't receive it. I don't know if this is a good place to pause just for questions, if there are any. And if not, I'll continue. All right. Okay, so in our factual problem, and I'll stop either here or here. So if you do have a question, you can sort of think of it before I get to the theoretical guarantees section, maybe. Okay, so in our factual problem, we don't get to see the counterfactuals on everyone. So instead, what we get to see is an IID data set consisting of n copies of baseline features. The intervention people receive, so we'll say that A is equal to little a star if they receive the intervention of interest. So for example, if the face was smiling in our main example, and then we get to see an outcome. And so in our main example, remember that outcome is like an image of a face. And we're going to suppose our counterfactual distribution is identifiable through what's known as the G formula. So this is a common expression in causal inference that on the left-hand side, we have our counterfactual distribution. On the right-hand side, we have some transformation of the distribution of our observed data. And that transformation sort of takes this form where we look at conditional probabilities, and then we just sort of average them out across the marginal distribution of features. If you don't like thinking about causal inference and you'd rather think about a missing data problem, that's fine. Then I would tell you that this identifiability result that we have here is just the standard identifiability result you get if you assumed if Y was missing for some individuals, and you assume that A equals A star encodes that the observation is not missing, and the outcome we're missing at random. So this is just sort of a standard missing at random identifiability result. In a causal inference setting, the sort of main condition that we require here is no unmeasured confounding. So there can't be any confounders beyond those in X of the effect of A equals A star on Y. And then we also require positivity, which just means for each value of the baseline features X, there's some positive probability of receiving the intervention. In our smiling faces example, there can't be sort of any types of people as defined by their baseline features who would never be smiling in our data set. If such people did exist, we'd have to extrapolate in order to figure out what a smiling face would look like for them. Okay. Okay, so what I'm going to do now is I'm going to take the algorithm that we already saw together. So there's nothing new here so far. This is exactly what we saw earlier. This is our counterfactual or our generative modeling algorithm. In the Oracle case where we actually got to see the counterfactuals on everyone. And I'm just going to take that and I'm just going to make a few modifications. So take the thing we saw and everything that's in red here, I'm going to change, and I'm going to change nothing else. And then we'll arrive at the proposed approach. Okay, so first is very superficial. I'm just going to change the name. So we're not in an Oracle setting. We don't get to see counterfactuals on everyone. So our approach is called DoubleGen. And this is just a doubly robust approach to doing generative modeling. Sort of more substantially, we're going to allow for sort of the input of different data. We don't require the counterfactuals on everyone, but we do require tuples of baseline features, intervention, and outcome on everyone. And we get an IID sample from this distribution P. We're going to require a choice of generative modeling framework, and it can be sort of the same choice that you would have made in the Oracle case. So if you were sort of training a language model and you wanted to use autoregressive language modeling, you're still going to do that. If you were training an image model, you want to use a diffusion model or flow matching, you're still going to do that. You don't have to change your framework in order to use our approach. You do, however, have to change your risk. So remember, the risk before that we were using was just the empirical risk based on some loss function L. That same loss function L will appear in our risk as well, but we're going to sort of have to deal with the fact that we don't get to see yi star, that counterfactual outcome, on everyone. And the way we do this is just by replacing the risk by an augmented inverse probability weighted risk. And that risk just takes the following form, and I'll sort of talk us through on the next slide sort of what some of this notation, this alpha n and this psi n mean. Roughly speaking, you can think of alpha n and psi n. They're just things that we're going to use our data. They're nuisance functions that we're going to use our data to learn. And again, I'll talk you through what exactly they are. But broadly, this is just an augmented inverse probability weighted estimator of our risk to account for the fact that we didn't get to see yi star, the counterfactual, on everyone. And finally, we're going to return a transport map. Remember that transport map is just sort of the sampler that we obtain once we've learned that theta, say those neural network weights. So for autoregressive language models, that's just going to be sort of a next token sampler. For diffusion models, it's like a stochastic differential equation solver. And that transport map remains completely untouched once you've learned theta using the new risk. So you use sort of the exact same code as you would have used in a non-counterfactual setting in our counterfactual setting. So all I've done here is I've taken the risk from the previous slide. This is that augmented inverse probability weighted risk that we use to deal with the fact that we didn't get to see the counterfactual yi star on everyone. And I'm going to explain what the two nuisances are. Okay, so as I said, you're going to have to learn two things. So the first is an inverse propensity. So this is just 1 divided by the probability of receiving the intervention. For example, smiling, conditional on baseline features X. There are many ways to estimate this. There's nothing sort of specific to generative modeling here. This inverse propensity comes up all the time in causal inference settings. So you can use stable balancing weight approaches based on stable balancing weights, Reese regression, logistic regression to estimate the probability, etc. So there are sort of many ways of doing this, and it's sort of completely standard in the causal literature. So we could just sort of pull standard software for doing this. Perhaps a little more interestingly, we have the outcome generative model. So here, if we look at our risk function, we're integrating out over these sort of samples of U. So this psi-n is going to be noise essentially, and what we're doing is we're training a second generative model instead of the marginal one that we're mainly interested in. We're training a conditional one, so conditional on the baseline features that someone has. This psi-n is going to take as input noise U and then generate a face that looks like that sort of is consistent with those features. So for example, I'm oversimplifying a bit. If X is young man here, and I feed in one value of U, then I'll get sort of one face of a smiling young man. If I feed in a new U, I get sort of a different face. If I feed in yet another U, I get yet another face. Okay, so we're training this generative model. Sort of cards on the table here. This is a harder problem. Training this outcome generative model, which is conditional, is a harder problem than the marginal problem that we're actually interested in. However, sort of downstream, we're going to have this remainder term in our regret bound that's going to have this sort of second order nature where we sort of don't have to pay the full cost of solving a harder problem. So we'll see that remainder term later, but maybe it's just worth keeping in mind that even though we're solving a harder problem, if we get this wrong or sort of don't do very well on it, we can still do very well on the marginal transport map that we're actually trying to learn. Okay, I'm going to do a bit of relationship to existing literature. We're not the first people to think about counterfactual generative modeling. The first approach that I'm aware of that did it in a sort of modern way, where the goal up front was the generative model or learning that transport map, would be what was known as causal GANs. So GANs were sort of a very popular method about 10 years ago, generative adversarial networks, for training generative models. And this causal GANs paper basically took the GAN machinery and used it to generate counterfactuals. This has also been done with normalizing flows, variational autoencoders, and diffusion models. All of these are iterative approaches. And what do I mean by that? So first, they sort of will learn a generative model for generating features. Then they're going to intervene. So they're just going to say, okay, we want everyone to be smiling. And then they're going to train a conditional generative model for the outcome conditional on receiving the intervention, which just means they subset the data to those who receive the intervention, and the features. And then they're going to generate outcomes conditional on features that they generated earlier. And essentially later on, they just throw out X and A star because we're only interested in the marginal model at the very end. So it's iterative in that first they learn to generate features, then they learn to generate the outcome conditional on everything else. There are also approaches that do what I'm calling joint generation, which just means they learn to generate sort of from the joint distribution all at once of X, and then this intervened A equals A star and Y. Again, sort of all focusing on particular generative modeling strategies. And finally, there are what are known as direct approaches, and there, the one that I'm familiar with is inverse propensity weighting from this Wu et al. 2024 paper, where they use a very similar risk to ours in a sort of a restricted class of problems that they look specifically at likelihood-based approaches. But within that restricted class of problems, instead of using an augmented inverse probability weighted estimator, they use an inverse probability weighted estimator, which turns out to be more robust, and you get sort of weaker results for it. But I can talk about that when I get to the theoretical guarantees section. So broadly, unlike the approach we propose, DoubleGen, these existing approaches mostly only apply to specific generative modeling paradigms. So sort of there's an approach for GANs, there's an approach for diffusion models, et cetera, but there's sort of no one stepped back and told the whole story that actually there's sort of a very simple and common approach, of which DoubleGen is one, to generate counterfactuals. There also sort of lack theoretical guarantees. So there's nothing like a generalization bound or a divergence guarantee for the learned transport map. And these approaches are also only singly robust. So they're either sort of relying on outcome modeling or propensity modeling. But if you get either of those two things wrong, then the final learned transport map will be wrong. We're also not the first in the causal literature to use augmented inverse probability weighted risk estimators. So a popular class or popular set of problems for doing this is in conditional average treatment effect estimation, the so-called DR learner. is one such example, going back to Vanderlaan in 2006 and 2013. There are also It's also been used in other problems, including classification, learning survival functions, and longitudinal means. And then beyond these sort of conditional estimates, this has also been looked at a bit more generally. Probably the most general paper would be this Foster et al. 2023, where they introduced something called orthogonal statistical learning, which is basically just a general approach to doing statistical learning in the presence of nuisance functions. But of all these papers, all of which are very nice, none of them have sort of studied generative modeling problems. Okay, so now moving to our theoretical guarantees, and I'll pause one last time for questions. It's the last time till the end. All right. Okay, so moving towards our theoretical guarantees. So I'm not going to go into a ton of detail. I would encourage you to take a look at the paper if you want to sort of see our detailed guarantees, but I'll go sort of high level here. So broadly, the main objective of our theory is to make it easy to sort of use results from the generative modeling literature. Recent papers have shown that diffusion models under some conditions can be minimax optimal distribution estimators, and that similarly flow matching can also be minimax optimal, or this is always sort of nearly up to these log factors. I would say unlike sort of maybe more traditional statistical learning problems like regression estimation or density function estimation or something, where it's sort of, I don't want to say easy, but I would say it's sort of relatively classical to show that different estimators are minimax optimal. In these generative modeling problems, there are a lot of sort of non-regularities that make sort of the minimax optimality guarantees in these papers rather hard to establish. This includes things like the score functions that a diffusion model works with tend to blow up near time zero when you're reversing through time. And then they also deal with the fact that the estimator class is actually parameterized by neural net weights as well. And so the arguments here end up being sort of very delicate. And so to the extent possible in our causal setting, we don't want to have to reproduce these arguments from scratch. That would be a lot of work and very difficult. So our goal is essentially to build directly on these non-causal works and sort of develop our theories as sort of a wrapper to them. And so we very much built our theory in such a way that if a new generative modeling procedure comes along and one wants to generate counterfactuals with it, then provided someone has already established theory about that non-causal approach, you can sort of plug it into our theoretical wrapper and then develop theory for the causal approach. So that's sort of how we built our theory, to sort of let non-causal people think through all the difficult details, and then we can sort of give a causal wrapper to it. This is just essentially to avoid having to do difficult work twice. Okay, so we'll break our analysis into two steps. So the goal of the analysis is going to be to show that the true and estimated counterfactual distributions are close. So this just means that if we look at the distributions, the true counterfactual distribution and the estimated ones, the theta n, those are, say, the neural net weights that we learn. And then this p theta n is the distribution that we get from the sampler. It's the push forward of the sampler when we push noise through it. And we're going to require that this be less than some rate function. Okay, this is a case. I'll give an exact example towards the end of this subsection of the talk where I tell you what the rate is, but you can usually think of this as like n to the minus alpha for some appropriate alpha or something. And our strategy is going to be twofold. So first, we're going to take the divergence measure, and we're going to try to bound it by some transformation of the generalization error of the risk minimization problem that we sought to solve in the first place. And then we're going to bound the generalization error. What you'll notice for the first part of this strategy is that if we want to bound the divergence by some function of the generalization error, this really has nothing to do with our counterfactual or our causal problem. Remember, our problem is essentially that we don't get to see the counterfactuals in everyone, so we need to sort of figure out how to work around that. But this is all at the population level. And so actually these sort of bounds where you upper bound the divergence by the generalization error already exist in the literature, in the non-causal literature. And so we can sort of directly just look them up and port them over to our setting. So for flow matching, if the divergence is the 2 Wasserstein distance, and you choose the exponent to be 1/2, then we can upper bound the divergence by essentially the square root of the generalization error. Diffusion models, you work with total variation distance, sort of same story. Autoregressive language model, you work with KL divergence, and then you sort of just definitionally you recover your generalization error. So all of these results are they exist. We don't need to do anything. We just sort of pulled them from the literature, and we're done. Okay, so this is sort of the first part of our wrapper. The second part's more involved, but still sort of relatively manageable. So for the second step, we now need to study the generalization error. And I'll sort of walk you through and build up to our main theorem regarding the generalization error. So our goal here is going to be to provide a generalization bound for the empirical risk minimizer. Admittedly, this is a bit of an oversimplification. If you learned neural network weights theta n using stochastic gradient descent or something, you're of course not exactly recovering an empirical risk minimizer. But this is sort of one of the many possible relaxations that people in the literature will use in order to try to get some theoretical understanding of what will happen in these contexts. Okay, so we provide this bound for the empirical risk minimizer, where we're just minimizing our proposed AIPW risk. And I'll show, just to remind you, that AIPW risk takes this form. There's nothing new here. This is the risk we saw on that earlier slide, where we took the usual empirical risk and then we just applied an AIPW transformation to make it tractable, even though we don't get to see the counterfactuals on everyone. Okay, and what we're going to do is we're going to relate our empirical risk minimizer, at least its performance, to one for the oracle problem where we actually got to see the counterfactuals on everyone. So our theory is going to sort of explicitly relate the two. And our generalization bound takes the following form. So under the same statistical learning conditions that you would use for the oracle problem, and we sort of explicitly state those in the paper, then with high probability, our generalization error is something like an approximation error term plus a rate term. This involves the entropy of the class that theta belongs to. You can look in the paper for more details. Plus this term that's a product of two terms. It's sort of the error for how well you estimate, or sort of the error for the inverse propensity, and then the error for the outcome model. Okay, so because we have a product of two errors, if both are small, then the product will be doubly small. And it's in this sense that the fact that we solved a harder problem by estimating this conditional generative model psi n for the outcome model isn't going to cause us problems because we're getting to multiply that small number by a second one. So the leading terms on the right, this is sort of exactly the generalization bound you would get for the oracle problem. The cost that we pay for not getting to see the counterfactuals on everyone is having to estimate these two error terms. And that final term turns out to be doubly robust. Again, so if either of those errors is 0, then the product is 0, sort of a standard double robustness result. So if we take that sort of main result and our argument for bounding the divergence of a counterfactual generative model, and we take that and we apply it to training a diffusion model, we're able to show that counterfactual diffusion models are doubly robust when you use our DoubleGen procedure. So if we parameterize the scores via an appropriate neural network class that we make explicit in the paper, we use the same one as in this non-causal paper, then we can bound the total variation of our learned counterfactual distribution and the true counterfactual distribution. Here we're looking in a d-dimensional hypercube, and we require that the density function that we're estimating be Besov smooth, and on top of that, we're pulling the regularity conditions from this paper. We also require a little bit of smoothness on the boundary. And what we get is that we get a sort of minimax optimal rate over the Besov smoothness class up to a logarithmic factor. This is the same logarithmic factor that they got in this paper, plus or minus a half or so, plus a doubly robust error term. Okay, so we're indeed recovering sort of exactly what you would hope in the oracle problem, this sort of near minimaxity result, plus an additional bound that's quantifying how well we estimated those nuisances. Okay, and if you end up looking through the theory in the paper, the way you'll see we prove this result, we basically go back to our main result from the previous slide. As we mentioned here, we use the same statistical learning conditions as for the oracle problem. So then we can just look at other papers who have already established these conditions for the oracle problem, and then we just plug them into our generalization bound. So the proof actually doesn't end up being very hard. The sort of original paper that we borrowed from was like 50 pages long just to establish those conditions, but we essentially get to cite them carefully in order to establish this result for diffusion models. Okay. So I'll show you now a couple of experiments. I'll start with image experiments, high level, then I'll show you one with text. So just to recall what we saw before, we have a celeb data set, images of celebrities. We have baseline features on everyone in the data set. The faces who are smiling and those who are not smiling tend to differ according to some attributes. So the smiling rows and not smiling rows are different for these attributes. And so what we do in our experiment is we train 2 diffusion models. We train more than that, but I'm just going to show you 2 to start, where first we only use smiling instances. We basically threw away all the not smiling faces, only use smiling instances and a standard diffusion loss function. And then we used all instances and a DoubleGen loss. And exactly as anticipated, when we sort of naively threw out the not smiling faces, didn't try to do anything causal, we did generate smiling faces, but those smiling faces sort of recovered the feature attributes from this top row. Whereas when we used all instances and our loss, we sort of recovered the attributes on the bottom row. And I'll just give a snapshot here of some generated images. So top row, we have images generated by the sort of naive model that only trained on smiling faces. Bottom row, we have images trained using our DoubleGen model. There's a coupling here. So the way we coupled these images, a diffusion model takes as input Gaussian noise to start and sort of slowly denoises it until you get back to a face. We essentially just set the same random seed for the 2 models, which means we fed them the same random noise. And then also in the SDE solver, we use the same random seed for the solution. And in this way, sort of vertically, so this, this was maybe seed 1, this might have been seed 2, et cetera. And so what we see here is that for some of the faces, they're essentially the same, a little bit different, but almost the same, but some sort of meaningfully switch. And typically when they switch in ways that are sort of trying to sort of correct some of the changes up here. So here we switch from blonde to not blonde, for example, and lipstick to not lipstick. And so I put stars here. All the star tells you is just trying to draw your eye to images that are sort of meaningfully different. If you want to look at the paper, we include 200 random images from each model coupled in this way, so you can sort of directly compare how they change. We also look at quantitative measures. So here we looked at popular measures for Shea and kernel arc face distances. These are just sort of common in image modeling to see how well images reflect some target distribution. Smaller values are better. And what we saw compared to the naive model, we standard everything. So the naive would be just have 1. DoubleGen tended to perform quite well. So it tended to outperform the naive model. And then what we also did is we compared to sort of plug-in methods and inverse probability weighted methods. So sort of natural alternatives to our use of an augmented inverse probability weighted risk. And we tended to also outperform those methods, just meaning we sort of obtain smaller values according to this metric. One more experiment. The final one uses text. So this was a semi-synthetic experiment so that we actually knew the ground truth, or at least had a random sample from it. So here, we used the Amazon Reviews 2023 data set. So the data set consists of roughly 500 million Amazon reviews, along with product category and other metadata. We use that metadata as baseline features. The synthetic part of the experiment was the intervention. So we created our own intervention in such a way that we could then know the ground truth counterfactual distribution. And we define the intervention in such a way that there was a lower propensity for some product categories, most notably books. So books were less likely to receive the intervention than others. And I maybe remember that because I'm going to show an experimental result where the fact that there was a lower propensity for the product category books is actually going to matter. So sort of a generic outcome in these setting, I chose 2 of the 500 million outcomes. We took the star rating of the products, we stuck it in front with a colon. So we first have sort of the product rating out front, and then we have a little bit of review text. And I don't remember where we cut it off. Call it 125 tokens, but I really don't remember exactly how long the reviews were. But they're all relatively short, at most like a paragraph or 2. Okay. To train a language model, unlike the diffusion model from the last experiment that we trained from scratch, here we didn't. We fine-tuned the Llama 3.2 1 billion parameter model. And to fine-tune it, we added 5.5 million trainable parameters using LoRa layers, low-rank adaptation layers. We froze all the other parameters. Okay. And so broadly speaking, the naive approach that just sort of only used the reviews that received the intervention, and our DoubleGen approach that tried to do something causal and correct for possible confounding. Broadly speaking, they generated pretty similar reviews. So there's just as before, there's a coupling. We just set the same random seed before we generate a review. And what you'll see, my son loves to use the game and can play for hours. Thanks for a fantastic app purchase. These 2 reviews are exactly the same up to the word, app versus game, but essentially they're the same. And similarly, we have this review about, I don't know, skirt and shorts, but overall, it's essentially the same review. In order to sort of look for where DoubleGen sort of might improve upon the naive approach, because we had a synthetic intervention, we actually knew what kind of confounding to expect. And in particular, remember that books were less likely to receive the intervention than other product categories. So what we did is we just counted the number of times the word book was used in our generated reviews. And so the naive approach tended to underuse the word book. It was about in 0.24% of reviews generated by the naive approach did the word book appear. And this compares, it was roughly 4.5% in truth. Remember, semi-synthetic experiment, we knew the ground truth. So we knew that about 4.5% of the reviews should contain the word book. And then when we look at the DoubleGen reviews, they are almost bang on for that. They had 4.4% of reviews had the word book in it. And if you sort of look at the coupling, I find it sort of fun. You can sort of see they suddenly diverge. So this is amazing, blah, blah, blah. Whereas ours says, this book was amazing. And suddenly, the blue reviews talking about a book and the latter ones talking about something with batteries. So not a book. Similarly, it's an okay quality mask. It's an okay book. So indeed, we were correcting for confounding here, where essentially books will be underrepresented if you just look conditionally on receiving the intervention in this particular data set. Okay. So I have just a brief discussion. The sort of first part I already alluded to, I guess, when I was talking about the identifiability result. But I've sort of framed this talk around sort of causality and looking at counterfactual distributions under some intervention. The sort of exact same DoubleGen approach can be used if instead of thinking about counterfactuals, we just think about missing data. So we have an outcome that's missing at random, and we essentially have some x's corresponding to some y's, and we have some x's where y is missing. And in this case, you can just use our approach sort of exactly as is if you define A equals A star as observed. And you can sort of apply the same AIPW risk estimator. It might be the case where you have missing completely at random data. And in that case, you sort of exactly recover the simplified setting considered in the prediction powered inference literature. So this is sort of, if you wanted, you could label this as like a PPI method for a generative model. It's sort of the risk function is exactly the same as the one you would recover from recent improvements on prediction powered inference. Yeah, so another detail that I swept under the rug that maybe is just worth noting. So in practice, LLMs don't actually tend to sample from the learned distribution. So they are indeed estimating the marginal probability of the first token, the conditional of the second given the first, et cetera. But when it actually comes sampling time, they don't directly sample from that typically in practice. It turns out that you can get sort of qualitatively better sequences generated if you actually sort of oversample the high probability tokens. There are different ways of doing this. Sometimes they'll sort of focus on the top K, say the top 100 tokens, and then they'll just sample one of those. They sort of throw out the low probability tokens. Sometimes they have some temperature parameter for deciding. In principle, you can do the exact same thing if you use something like DoubleGen in our counterfactual context, but then you do lose the very sort of clean relationship between the generative modeling scheme that you're learning and the downstream transport mapped to the counterfactual distribution of interest. And then finally, so I've focused today on sort of marginal learning to generate marginal outcomes, counterfactual outcomes. It's sort of straightforward to generate conditionally on some subvector V of our baseline features X. There are sort of very simple changes you can make to the loss functions. The theoretical results essentially go through unchanged in these contexts too, but it would have sort of had to carry more notation through the whole talk. So I didn't do this. But something sort of maybe interesting for future work. That's all from me. So the papers on arXiv is under the same title as the talk, and I'm open for questions.
Okay, thank you very much, Dr. Luke, for this excellent talk. Now let's stop recording so we can open the floor for questions. Okay.